Okay, so in this video, we're going to talk a little bit about the model of the atom and kind of get into a deeper definition of electrons, protons, and neutrons. Again, atoms are made up of three subatomic particles. A subatomic particle is just a particle that is smaller than an atom. So those would be our electrons, our protons, and our neutrons. So remembering that atoms are made up of that dense sphere of positive charge, all the positive charges in the center with most of the mass, and then around the outside here we have the electrons floating around in what we might call the electron cloud. So a cloud of electrons floating around the outside, electron cloud. So again, the nucleus makes up 99.9% of the mass of the atom. Only 0.1% of the mass of the atom can be contributed to these electrons all around the outside. And those electrons are going to be tiny negatively charged subatomic particles. They are by far the smallest. So remember that 99% of the mass is made up, is being taken up by this nucleus. So that means every single electron around the outside, all of them added up together, account for that 0.1%. So they're super tiny in comparison, let me tell you. So they float around the outside of the nucleus in the electron cloud, so in that electron cloud, in that space around it. And again, they're a small percent of the overall mass of the atom. So lots of electrons flying around the outside. And I've been saying protons, but what in the heck are protons? So protons are going to be kind of the counterpart to electrons. So they are positively charged particles. However, they are much, much, much larger by a lot than an electron. So they're not the biggest subatomic particle, but they're much, much, much larger than an electron is. And protons are going to be in the nucleus. So electrons fly around outside in the electron cloud. Protons are actually in the nucleus, inside the nucleus of your atom. And neutrons are the other subatomic particles. So negatively charged electrons, positively charged protons, neutrons in the middle are not charged at all. So they are neutral, no charge, charge of 0. All of those are equivalent. No charge on the particle. And it's going to be slightly larger than a proton. So it's about the same size as a proton. So protons and neutrons are very big compared to our very teeny tiny electrons. So very large protons and neutrons, very small, teeny tiny electrons. Neutrons are only slightly bigger than protons. However, both protons and neutrons are kept in the nucleus of the atom, and it's only the electrons that fly around the outside. So you kind of end up with this like dense positive center surrounded by negative around the outside. So it's together that the protons and the neutrons make up 99.9% of the mass of the atom, rather than just the protons or just the neutrons. Again, both of their mass together, added together, makes up that 99.9% of the atom. So let's compare them just a little bit more. This whole time, for the last couple of chapters, we've been talking about choosing in a unit with an appropriate scale for what we're looking at. So now I'm going to start to introduce you to very small units that are going to be taking place on the atomic scale. So on this very teeny tiny scale, that's where we're looking to put our units for right now. So what we're going to use is, to measure the mass, is the atomic mass unit, or AMU, is how we will abbreviate it. So this was discovered by taking 1/12 of the mass of a carbon atom with 6 protons and 6 neutrons, okay? So kind of basically assigning each of those a mass value of 1. However, we figured out, and we know, that a neutron is slightly larger than a proton, and they are not the only thing taking up mass in our atom. We also have the electrons flying around the outside, which it only accounts for 0.1. However, 0.1 is enough to change our results in this case. So if you check down here and you check out the mass in AMU, you can see what we consider those masses to be. So you can see that each proton and neutron is slightly bigger than 1 AMU, even though often we approximate that mass to be 1 AMU. So you may hear me just say that they're 1 AMU because, you know, you could really round this number to 1. It's very close. However, check out this electron down here at the bottom. He doesn't even weigh half of what they do. He doesn't even weigh a tenth of what they do. He weighs a lot less. So electrons are teeny tiny in comparison to this. We've got 0.005 or 1. Those are two very different numbers, okay? So you may also want to look at it on the kilogram scale. So when we're talking atomic mass units, we're talking kilograms to the -27th. So again, we can see that the proton and the neutron, they're about the same mass. However, that electron is much smaller. So what you see the electron written down there as is 0.00091 times 10 to the -27th. There should be some huge alarm bells going off in your head. I'll give you a second to decide if you know which alarm bells I'm talking about. That's not actually in scientific notation, is it? Interesting textbook. That's not scientific notation. I'm looking at you. No, however, sometimes we choose to do what I call improper scientific notation to kind of show the scale of numbers. So even though we're looking at -27 or 10 to the -27 in our mass in kilograms, I can still very easily compare those numbers because look, we can say, hey, that 0.00091, it isn't even close to those other two because of the way it's written. You know what I mean? So this is really what the intent of scientific notation is in the end, is to be able to look at those numbers and compare them easily. So yes, it's not properly written in scientific notation. It's improper scientific notation, you might call it. But the thing is it gets the point and the intent of the numbers across. So we can see that that electron is much, 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 much smaller than the proton or neutron. We also have the charges listed over here on the right. So we can consider a proton to be 1+. We could consider a neutron to be 0. And we can consider an electron to be 1-. We'll talk about this a bit more as we start to get more in depth on this. But we always say 1+ and 1-, 2+, 2-, 3+, 3-, however many or however high your number is. When we're talking about electrical charge, or we're talking about like the charge on an ion or an atom, I've asked around. My fellow chemistry professors here have lots of the anecdotes of where some of this stuff came from. They know. I'm learning the stories myself. I get to kind of sit around the campfire and get to know some of these stories in chemistry. So I asked them. I thought they'd know. Not that none of us know. It's more of a notation to help tell numbers apart. So later on, we're going to talk about oxidation numbers. It helps us look at something and know whether it's a charge or an oxidation number or something like that. So it helps us tell it apart from other values. But other than that, I have no good reason why we have charge always written as 1+ instead of +1. We usually put the sign in front. If we're talking about charge, we usually put it after. You'll start to see me take that convention of putting the charge after. You should also take that convention of putting the charge after. So 1+, 1-, not +1, +-, unless we're talking about a different kind of number. So a little fun fact there for you. I don't know why, but that is why we do it. And it's most likely because of comparison with oxidation numbers. So if you think it looks a little funny, it does, but it's not a typo. So, as we're talking about electrical charge, just a little bit more here, let's get a formal definition going. So, an electrical charge is kind of inherent property of electrons and protons. It's something that's there. We know it exists. We know how it works. It's just a part of an atom, or in this case, a subatomic particle. So, it's just a property whether something is positively charged or whether something is negatively charged. That's it. I want to be clear here too, that don't get hung up on the words positive and negative as we move along. We arbitrarily picked it. So we could have said electrons are positive and protons are negative. We could have. That's fine. However, really what we mean when we're saying positive and negative is that these charges are opposite. So they are opposing charges. They are different from each other. So we kind of randomly picked positive and negative, but we chose them because they are words that mean opposite in our language. So it's either positive or negative, but don't get caught up on, oh, this must be some gigantic scientific reasoning as to why protons are positive and electrons are negative. Nah, we just chose that electrons are negative and protons are positive. That is what they are, and now you have to know that and you have to accept that fact, but don't kind of get caught up in the name game there. We also have some more information kind of about the nature of an electrical charge. So these are going to be some kind of things we can think about and do with our electrical charges. So there's 4 points here to describe the nature of an electrical charge. So first and foremost, as we've been talking about, it's a fundamental property of protons and electrons. It's there. Second and foremost, positive and negative electrical charges attract each other. Okay, so opposites attract. Sounds familiar. Heard it before. Holds true here. Opposites attract. So if you have a positive charge and a negative charge, they're going to attract each other. However, as we may have experienced with magnets, if we have 2 positive charges or if we have 2 negative charges, in that case, those 2 charges repel each other. So if I've got 2 positive charges, I try to bring them together. You can't bring them together. You can't force them. They're 2 positive charges. However, you've got a positive and a negative. They are stuck like glue right together. The last point here is a little subtle, a little important, but we'll go over it. If you have a positive charge and a negative charge, they kind of cancel each other out. So we can consider them canceled. So if we add a 1 plus charge and a 1 minus charge, they're canceled out. I'm sorry if I just clapped into your headphones. I apologize. So positive charge, negative charge, put them together. They cancel each other out. We consider it to be a neutral charge, a charge of 0. So if we're talking about no charge, we could call it 0. We could call it neutral. We could say no charge. So that's kind of the idea it means in the last point, is that if you have the same number of positive and the same number of negative, the electrical charge is neutral. So to sum it up, opposites attract, same charges repel. If you have 1 of each charge, they cancel each other out. And again, a neutral charge means neither positive nor negative, no charge. So that's kind of how we're going to think about it. So I'll continually be talking about positives and negatives and balances and, do you have as many positive charges as you do to balance each other out? So it's really important that you dig in and really understand this concept here. So now that we've spent a little bit of time talking about our subatomic particles, let's talk about what we do with them. So we've been talking about atoms and elements. We know that elements are pure substances. We know that they're made of matter. We know that elements are made up of one type of atom. However, how do we start to tell elements apart from each other? Well, we tell them apart by their number of protons. So each element has a specific number of protons. If you have that number of protons, you have that element. If you do not have that number of protons, you do not have that element. Each element is defined by its number of protons. So if the number of protons changes, the element that you have changes. Even if you have the same atom and you lose protons, it's a new element, okay? Changing the number of protons changes the element. Each element is defined by the number of protons it has. Later on, we're going to talk about what happens if you change the number of electrons or you change the number of neutrons in a particle. We'll worry about that later. You change the number of protons, you change the identity of your particle, okay? So that number of protons in an element is called an atomic number. So the atomic number, we could call that Z. We use the letter Z to represent the atomic number. So I could say, what is the Z of calcium? And you could tell me what the atomic number of calcium is. So the atomic number is the number of protons in an element. So this is going to be the big number that you usually see to kind of identify an element on a periodic table. So that's going to be this big number up here at the top. So this big number up here at the top is going to be the atomic number. So that tells us how many protons our element has. So the big whole number at the top of the box when we're looking at a periodic table identifies the number of protons in the element. Other things you might see about each individual element on the periodic table are their chemical symbol and their atomic mass. So the chemical symbol is just a shortened version of the name. Again, chemists are lazy. We don't want to write out the words all the time. It's a waste of time for us to do that. That's time that could be spent doing science and more experiments if we weren't writing down letters all the time. So we have some shortened versions of the chemical name to quickly denote the name of an element. These are usually only 1 to 3 letters long. Usually the 3-letter ones are man-made elements that we're fully confirming exist and that we can prove. Most of them are kind of considered to be, but we haven't fully decided what they are yet. So you won't really come across the 3-letter representative chemical symbols in this class. We're not going to mess with that. I've never once really thought about them more than their heavy elements on the periodic table. So I think we'll get by without them in this class. However, it is very important when we're talking about chemical symbols that you think about the capitalization of the chemical name you're using. So if you check out the periodic table, you can see that it's always the first letter that is capitalized followed by a second letter that is lowercase if there is a second letter. So it's usually one capital letter or a capital letter followed by a lowercase letter. So you have got to be absolutely certain that that is how you are typing it. It is wrong if you write a lowercase letter. Like if you write a lowercase c for carbon, you're wrong. That is not what the chemical symbol is. There's no, oh, I just didn't think about it. Oh, I didn't hit the space or the shift button to capitalize my C. I'm sorry, it's wrong. That is not the chemical symbol for carbon. The other thing is why we have to be so careful about the capitalization is this. If we look down here at my example on the screen, I have 2 different things written with the letter C and with the letter O.